Hello again. So we find ourselves now at the end of chapter 7. And technically, this is where I would cut it off and move into chapter 8 if we were following Strogatz to the letter. Unfortunately, I disagree with the presentation at this point. There's a topic at the end of chapter 8 which I feel actually fits really, really nicely, at least at an introductory level here at the end of chapter 7, as we talk about the stability of limit cycles. So at this point in our exposition, in our analysis, we have stated that limit cycles have stabilities, but we really haven't paid too much attention to actually classifying that stability. It would be a good idea for us to be able to detect the stability of a limit cycle in an analytic way, something that didn't depend on a numerical simulation. So, namely, if we don't have a phase portrait to look at, then our methods have no ability to determine the stability of a limit cycle, right? This is a global phenomenon, so we can't really appeal to derivatives the way we did for linear stability analysis back in chapter 2, talking about one-dimensional systems, and using the Jacobian for higher dimensional systems. So it's actually going to behoove us to come up with this analysis now so that we don't have to depend on a geometric argument to talk about the stability of a limit cycle, which, let's face it, is more hand-wavy than it is actually analytic, or than it is going to inform or prove our intuition. So we're going to be a little clever here. We're going to try to find a way to get stability out of a global phenomenon, which is easier said than done, but still doable. So I want to motivate it with the following example. We are going to consider this polar coordinate system. So you might recognize this. You might see that this is part of one of the systems that we considered before. And I'm specifically leaving off the r equals 0 component of this system because that's going to just be a little bit cumbersome to deal with. You'll see why in a minute. But I digress. In polar coordinates, we can actually solve this system explicitly. It is perfectly decoupled, and we can use some separation of variables to solve this guy explicitly for r, and even more simply, solve for theta. And you can verify this, right? The solution is going to be r0 minus 1 times e to the minus t plus 1 for r of t. And for theta of t, it's just going to be linear. It's going to be t plus some offset phase, theta 0. And notice, as as t goes to infinity, r is going to approach 1, right? We are going to approach the unit circle in this system, or at least we're going to approach the length, a distance of 1 away from the origin. But notice that theta is just going to keep wrapping around forever. This guy is going to just increase without bound. But remember, we're dealing with this in polar coordinates, so we're effectively treating theta in the modulus, in the minus pi to pi interval. So this is, or from 0 to 2 pi, so we're dealing with mod 2 pi arithmetic. So we're only ever stuck in thinking about theta as wrapping counterclockwise at a constant frequency of 1. So this guy, we could plot this, right? And you know what? If we did, so shapes, let me go ahead and do this real quick. Let me do it in black. There we go. That if we did try to plot this guy, then this is what we would see, right? We're in the XY plane here. And what we would eventually see if I did a circle, there's my eventual solution. Nope, there we go. And what's happening here is that this guy is an attractive limit cycle. And something's happening at the origin, but we're not talking about what's happening at the origin. So in this case, if I'm careful, sorry, I'm trying to draw and talk at the same time. A lot more easily said than done. But this is what's happening, that we are approaching the limit cycle at r equals 1. Right? So that's what this system is doing. No tricks here. So this system has a limit cycle, and we'd like to say that it is stable. So let's see what happens if I try to focus on that limit cycle, or see what happens, or what's happening in some slice near the limit cycle. And specifically, we're going to make the observation that theta is, okay, it's up to mod 2 pi, that theta comes back to where it starts, right? So if I think about starting this at theta equals 0, then after every 2 pi units of time, my trajectory is going to come back to the positive x-axis, right, at that theta equals 0 location. Therefore, the solution is going to intersect the positive x-axis over and over and over again, always at 2 pi units in time. And the positive x-axis, we're going to go ahead and call this capital sigma. And sigma is going to stand for section. So if we take a snapshot, kind of like a strobe effect, if we take a snapshot in time, the solution passes through theta equals 0 mod 2 pi, and we can actually create a sequence of points along the positive x-axis. And that's what's happening in this little diagram down here, that on the left, we have what the system looks like in its totality, but on the right, we're seeing just what's happening on sigma. I should even label it as such, sigma. Okay, so sigma equals 0 cross infinity cross 0. Right, so this is the positive x-axis for all intents and purposes. And if I'm looking at a starting point at little a here, right, I'm looking down here in the phase space on the left. If I start at a, and I move that, or I flow that solution forward in time, then the next time I hit the positive x-axis, I'm a little bit further from the origin. And if I flow even further, go to c, well, c is going to be even further from the origin, and now it's starting to approach a distance of 1 from the origin. I wrap it around one more time. I keep flowing this forward and keep asking, where is the next point of the solution that hits the x-axis? Then that goes to d, and this sequence of points seems to be approaching 1 on the x-axis. And on the other side, if I start at a capital A on the right, if I start over here, and I flow that solution forward and ask, when does it hit the x-axis again? It hits it at b, and b is getting closer to 1. If I flow b further, I get to the location c, and those are getting closer and closer and closer to x equals 1. So what happens if I start on 1? Well, if I start at 1, then I'm on the limit cycle, and each time I flow forward through the limit cycle, I ask, okay, what's the next point that I hit on the x-axis? Well, I'm just going to keep hitting the point 1 over and over and over again. And if I wanted to put that in here specifically, p of 1 would be exactly equal to 1. And what I'm saying here is that we are defining a discrete map, and we're going to call this map P, on sigma, and we're going to use our knowledge of maps in order to study the smooth system. So this is one of the reasons why I wanted to talk about discrete maps so soon in the semester, is so that we could use what we know about them to study the smooth systems. And this is one of the more powerful tools that we have. We'll name it in a second, but notice what's happening here. There is but a single fixed point of this discrete map P, and it happens at 1, right? And that was exactly what I'm highlighting here, that P of 1 is equal to 1. No problem. And we expect the absolute value, right, the modulus of P prime at 1 to be less than 1, because we observed the fact that the limit cycle is globally stable when we ignore the origin, right? This guy is going to have to attract points. And we saw from our linear stability analysis that if our derivative was non-zero, then we could check if the modulus was less than 1, that would be an attractive fixed point. And if the modulus was greater than 1, then we would have we would have a repelling fixed point, a repulsor. Okay? And we can actually construct this P specifically, and this is why I chose this particular example, is because the solution is particularly susceptible to us analyzing it and giving us a concrete example of what this map looks like. And if we do that, we can construct P of x specifically for an arbitrary initial condition starting at r0, 0. And r0, remember, has to be positive, right? I'm not including the origin in this example, but I very well could. And we see that if we are to consider what's happening for that initial condition, starting at some location on the x-axis and then flowing it forward through this planar system, then the next time we're going to hit sigma, right, the positive x-axis, is when theta is equal to 2 pi. I'll do that in red. Right? When theta is equal to 2 pi, that is the next iteration of the map, which is exactly where that fixed point r, or that initial point r0 gets mapped to. So in particular, this red box is exactly what this map has to be. Right? If I'm going to take this guy and ask what happens when theta is equal to 2 pi, then I'm saying take my initial condition and map it forward 2 pi units in time. And that's exactly what I get on the other end, that this is the next location on sigma that this map spits out, or that the trajectory would intersect on sigma. And we can check. Look for the fixed points in this system. Sure enough, if I say let P of x equal x, then sure, I can show you that x equals 1 is the only fixed point for this system, which means my solution has to close up after 2 pi units in time. That would correspond to a limit cycle, or at least a closed trajectory. And more to the point, if P prime is going to tell us about the stability, then sure, take a look. This is a linear map, right? I can go ahead and just differentiate this guy and say, oh, no problem, the derivative is e to the minus 2 pi. E to the minus 2 pi is certainly less than 1, so the derivative of this map has an absolute value less than 1, which makes x star, right, the fixed point, equal to 1, right, that thing that's corresponding to the limit cycle, that turns it into a fixed point for the discrete map. Now notice the derivative is constant here, so I didn't have to actually plug in x equals x star to my derivative map because it's a constant, it's a linear, right, P is a linear map in this case, we got really lucky. But the point is that we have just found an analytical way to determine when a limit cycle is stable or unstable, at least to first degree. We've created something called a Poincaré map. So the definition goes as follows, right? The sigma, right, the intersection set that we were talking about, in this case it was the positive x-axis, that would be called a Poincaré section. In general, this is going to be a codimension 1 hypersurface that lives in your set, right? That way you can flow the remaining complementary one-dimensional trajectories forward and keep intersecting this guy in time. But let's see. The minimum time that it takes for x in sigma to return to sigma through the smooth flow is called the time of flight. In this case, tau was equal to 2 pi, right? It's how long it took us to take a trajectory and map it from the x-axis all the way around the origin and back to the x-axis. So it took us 2 pi units to do that. The Poincaré map, or P, the map P is called the Poincaré or first return map, right? And this is a major tool for us moving forward. The eigenvalues of P are called the Floquet multipliers, or sometimes just the multipliers. And these are telling us about the stability of our limit cycles, right? So this technique is actually useful not just for autonomous systems, that we showed up on top here, things that were time independent in the vector field. But this actually is useful to us in the non-autonomous regime as well. I'd like to go through that example fairly quickly. But we're going to go ahead and consider an RC circuit, right? So we just have a resistor and a capacitor with a, they just start off with some charge. There's an alternating current in here, right? That would be your EMF, right? The voltage that's being applied to the system. And we're saying that this is an alternating frequency. So for usual rooms, that's somewhere around 60 hertz, right? So usual circuitry in commercial residences or commercial buildings in the United States, that's somewhere around 60 hertz. And this equation can actually be converted into an autonomous system, right? Our usual trick is if the system is not autonomous, then we can just go ahead and treat the time variable as its own independent variable or its own state variable in the system, which is exactly where this second row of the planar system comes from. So we're going to go ahead and solve the original ODE for Q dot, and then give ourselves an extra dimension to get rid of the non-autonomity, autonomosity, yeah. It's time independent now, right? And that's the vector field is now time independent, and that's all we really care about for this. But we notice that because this theta dot can never equal 0 unless omega is equal to 0, then there are no fixed points for this system. There are no fixed points for this system. I want to make that abundantly clear. And plotting this numerically, you can actually see exactly why. Right? If I have Q across the x-axis and theta across the vertical, then it looks like this system wants to eventually be attracted to an oscillating solution. Betcha scholars of Math 57, right, of our usual ODEs class can tell you exactly what the solutions look like to this. And in fact, we'll see it shortly. But this is an example for when the voltage is 3, the frequency is 5, and the RC constant is 1/5. So the natural time scale is 1/5. And we can see, since theta takes on values on the interval from 0 to 2 pi, we can actually wrap this around the y-axis a little bit and join up. Let's see, where would it be? 2 pi would be somewhere way up here. And this would line up with theta equals 0 down here. And we can join these two together. Like we can cut and then glue along those two lines to show that we can do this, we can realize this system as living on the cylinder. Right? It's an infinite cylinder, right? R cross S1. And I turned it up vertically so we could see it a little better. But in this case, yeah, this is the Q axis, which is moving this way up and down. And theta wraps around in this direction. Right? So this is all that's really happening. We are trying to see what happens, right? We're gonna increase some abstraction to make some analysis easier. And notice that for omega equals 5, there are 1, 2, 3, 4, 5 humps on this thing. Right? I tried to make that accurate. Right? So this is a frequency 1 or a frequency 5 map. So period 1/5 or 2 pi over 5. Excuse me. But notice what's happening. We can still realize a Poincaré map. If we think about the section as being this theta equals 0 axis, right? So specifically the Q axis, both positive and negative now, the whole axis, acts as a Poincaré section, right? This would be our sigma from before. And notice what's happening. That as I start along any solution here, they eventually want to work their way down toward the red oscillating map, or the red periodic map, or function, shall we say, periodic curve. Same thing with this Q downstairs. This guy eventually wants to go toward the red periodic map, which is in our setting now, because we changed the phase space, this is now a limit cycle, right? It is a closed orbit moving along the cylinder. So we can apply the same analysis as before, and verify that the limit cycle does exist, right? It's a fixed point of the Poincaré map, and we can figure out its stability as well. So the ODE techniques that we learned from Math 57 can show that there is the following solution. Dear Lord, why would you ever want to figure out that solution? Okay, crazy, awful. But the point is that we can figure this guy out explicitly, right? So we know what the original solution to the ODE up here. Oh, shoot. I didn't want to erase that. I wanted to circle it, right? We know that that is the solution to the original ODE, right? And once we know that solution, we can start constructing the Poincaré map. The time of flight is a little bit different here. Remember, theta is now equal to an arbitrary rate. But if we think about our d theta dt equation and solve it for dt, we can actually figure out how long it's going to take, right? It's going to take us one period here. So from 0 to 2 pi in theta, we only have to travel 2 pi over omega in time in order to come back to where we started. Okay, so this means that we have a way to figure out the time of flight, which is right about there. Okay, so that means all I have to do to figure out the Poincaré map is to plug in my initial condition and then say where that initial condition goes after 2 pi over omega units. And you can show, just like I do here, that this is what the Poincaré map has to look like. And you can verify this has a fixed point at this nasty value here, but it's all in terms of known quantities, right? In terms of the amplitude of your voltage amplitude, its frequency, and the natural, so the resistance and capacitor, right? The natural time scale for the system. So therefore, the fact that there's a fixed point here means that there is a limit cycle, and so we've seen the hint of it this whole time geometrically, and we can now verify it analytically. And that's the whole point of this technique, right? And we can ascertain the stability of this limit cycle by differentiating this map, which, strangely enough, again, is linear. Remember, this is happening in Q as our independent variable. This whole mess on the left-hand side is a constant. Happy day. Very, very happy day. So that constant differentiates away, and the only thing that's left is this e to the minus 2 pi over omega RC. And that is definitely less than 0 because all of those constants in the exponent are positive. So that means that the limit cycle is indeed stable. Right, so just like we were able to show geometrically, or to kind of guess at this geometrically, we now have a way to show this definitively, right? The flow K multiplier is e to the minus 2 pi over omega RC, which is less than 1, so the limit cycle is stable. Now, this construction does move into higher dimensions, and the analysis does get a little more out of reach, right? Usually, Poincaré maps are impossible to construct explicitly. So why bother talking about them? Well, because they are very strong geometric tools. So as much as they are an analytic way of discussing the stabilities of limit cycles, we often see them used in a geometric setting. Oh, and I just realized I missed a crossing here. Shame on me. That goes over. Yeah, right there. Voila. Okay, now it's better. Sorry. But yes, we can use these guys in a geometric setting and use their analytical properties to make strong analytic arguments as to why limit cycles would have to exist or to figure out what their stabilities would be. And we're going to see how this is used when we start talking about the Lorentz system. Okay? There is a nice geometric way to study that system, but the Poincaré map actually makes a return there. No pun intended. But it does. We do come back to this, and we want to be able to use the analytic properties of that map to study that limit cycle, or to show that there are limit cycles in the first place. Okay? And so also, if you're wondering what a negative Floquet multiplier might look like, think about dynamics on the Mobius strip. And that should wet your whistle. All right? I think that's all I want to say for this section. But the Poincaré map is going to be a great analytic tool for us moving forward. So I'll make sure I have some exercises for you in the homework that study it in a little more detail. But otherwise, I think that's all I want to say. We are officially done with Chapter 7.